Okay, we are going to continue on with our practice diploma questions for Unit A on chemical equilibrium. Now we're going to continue on with question number 36. The other questions are on a previous video if you want to go over them. So we're just going to continue through. There's only a few questions left of this practice diploma to go through. So question number 36 says, a solution containing the ammonium ion is mixed with a solution containing the hydrogen carbonate ion. Okay, it says the forward reaction, the Bronsted-Lowry base, and I'm going to underline that word base, is blank, and the conjugate acid is blank. So the first thing that we can do when we're looking at this type of question is if we know what a conjugate acid and base is, it should be an entity that has one extra proton if it's an acid compared to the base. So it shouldn't be two different substances completely. It should be only different by a single proton. So when I look at, for example, letter B, I see that I have my hydrogen carbonate, and this is not its conjugate acid. So there's no possible way that B could be an answer. Okay, inversely, when I look at question or letter C, I notice the same thing. These two things are completely separate entities. Therefore, they are not conjugate acid-base pairs. Okay, the two other options listed, okay, when I look and I see my ammonium and my ammonia, okay, that is a conjugate acid-base pair. And when I look at my A, I also see a conjugate acid-base pair. Now, there's two other ways that I can rule out the incorrect answer. Now, if I look at letter D, it looks like my letter I, okay, can be it can be a proton donor. Okay, it has 4 protons that it can donate. Therefore, this would actually be the conjugate acid of ammonia. So when I look at NH4 positive and NH3, well, NH3 is actually the conjugate base of this acid. Therefore, the answer has to be A, but there's another way of looking at it. That was just simply ruling out by what I know about conjugate acids and bases. But when I look at what is listed here, okay, I have my ammonium ions, I have my hydrogen carbonate ions, and I also have water molecules present there. So when I look at my chemistry data booklet, okay, which I will go to right now, and I check out and I see where on my chemistry data booklet do I have these entities listed, and I see ammonium is right here, this guy down at the bottom, and my hydrogen carbonate here is as an acid is here. So what I see is that my ammonium is a slightly stronger acid than my hydrogen carbonate, and it's definitely stronger than water. So my ammonium is going to be my strong acid, and it looks like my hydrogen carbonate is going to be my strong base. It's the one that's lowest down on my table when I compared to water, for example. So when I go back, okay, there we go. My strong acid is my ammonium, and my strong base is my hydrogen carbonate ions. So when I look at this is my base, this is my acid, and when I get my conjugate acid, which is what is formed, I get H2CO3 and ammonia, NH3. So this is my conjugate acid, and this is my conjugate base. So when I'm talking about my Bronsted-Lowry base and the forward reaction, that's this guy here, my hydrogen carbonate ion, and therefore its conjugate acid is A. So there's a few ways that I can go about solving this. If you want to solve by deduction, you can do that. That was the first way I did it. Or if you want to solve based on acid-base principles, that was the second way I've gone through that answer there. Okay, let's move on to question 37. It says, which of the following rows identifies the stronger acid and the side of equilibrium that is favored? Okay, so when we're talking about the stronger acid, when we look at the letters listed, I'm comparing either HNO2 or C2H5OCOOH, which is lactic acid. So when I go to look at my data booklet, this is how I'm going to tell which one is the stronger acid. I'm going to look for my my lactic acid, pardon me, and my nitrous acid. So I see nitrous acid is here, and I see my lactic acid is here. So when I compare the two, my stronger acids are always up to the left. So my stronger acid is nitrous acid for this question. Okay, and then the reaction favored, let's go back to see that again. So, well, I know my stronger acid is my nitrous acid, so I'm going to cross out letters C and D. And when I look to see which side is favored, well, if I take a look at that, I have to see when I'm comparing my lactic acid to my nitrate ion, or my nitrite ion, pardon me, I need to compare those two. So my lactic acid is here, okay? My nitrate ion, let me just get to new color here. So I'm comparing this guy here in green and this guy that I've circled again in green, and I'm going up like this. Now, if you remember, when we went through this the first time, we would say anything that is a strong acid, there we go, to a strong base. Okay, this is what we would say is products favored. If we have a strong acid down to the left and we find our strong base up to the right, this is reactants favored. So because our arrow is pointing up and to the right over here, that means that when we go back to this, it looks like our reactants are favored and HNO2 is our stronger acid. So the correct answer for 37 is in fact B. Okay. Let's take a look at this question, number 38. Let's read the question again here first. So the Bronsted-Lowry equation that represents the reaction that favors the products. Okay, so this is interesting. We need to find a reaction that favors products. And the one thing we need to check is to ensure our Kas are in order, in numerical order, from your stronger acid being at the top and your weaker acid being at the bottom. And the way that we do that is the greater the Ka value should be nearing the top of our chart. Now, that is how your chart is set up in your data booklet, so it should match that. And we see here that our greatest number is at the top and our smallest number is at the bottom. So this is in order. Now, when we look at this, we still follow this sort of method on my right hand side here, where my strong acid, if it's above and to the left of my strong base, it's products favored, and strong acid up to the right is my strong base is reactants are favored. So we want to make sure that our products are favored, so we want to ensure that our strong acid is above our strong base. So if I have my lactic acid, which is here, let's zoom in a little bit here. Here I have my lactic acid reacting with my glycolate ion, which is this thing here, okay, which would mean that my arrow is going up and to the right part of me. So this reaction would not be a forward reaction favored, so or the products favored. So let's take a look at C7H6O3, which is this guy here, salicylic acid, reacting with C3H5O3. Now this arrow is down and to the right, so this guy looks like it's most likely our best answer here, but let's just double check that the other answers don't give us a possible answer as well. So C7H6O3, which is this guy here, and let me just we will just highlight that this guy is the one we've chosen so far. Okay, when we look at C7H6O3 and we're reacting with this guy, again, that arrow is up and to the right, so that's not an answer. And then C2H4O3 reacting again with that chloroacetic acid conjugate base. So B is our best answer there. Let's take a look at the next question. Oops. Pardon me. So, we're going to, again, read our questions here. So it says 39. The amphiprotic species listed above are, remember, amphiprotic means an entity that can both donate or accept a proton. So when I take a look at my amphiprotic entities, okay, I know that when I take a look, I need to make sure that an entity can both accept and donate a proton. So when we take a look, okay, my H2O, I know, can turn into either OH minus or it can turn into H3O positives. That means that it can either be a proton donor or a proton acceptor. Okay, now number 2, well, it appears as I can have a proton acceptor. We know that hydroxide ions are a good proton acceptor. They're a good base. However, this can't donate another hydrogen, or it doesn't like to donate another hydrogen. Also, we know that this base, our hydroxide base, is our strongest possible base. So this oxygen wants to hold on to this hydrogen more than any other entity that we know of. So this guy is not going to want to donate that hydrogen. So we're just going to put a line through that guy there. Okay, number 3. We can definitely accept a proton here, but there is no hydrogen to donate. There's no hydrogen there to give another substance. So we know that 3 cannot be it. It does like accepting the protons, but there's nothing to donate. Number 4 here, we see that it can accept a proton, okay? It can become, have another positive charge added onto it because it has a negative charge. And also this hydrogen here could also potentially be kicked out and donated. So 4 is a good possible answer as well. When we take a look at question, or number 5, we see that it has a negative charge, therefore it can be a proton donor or proton acceptor. And then this hydrogen means that it can also be a proton donor. So we have that one checked off as well. Okay, and when we look at question or number 6, we see that it can definitely be a proton donor. We have 2 hydrogens that it can donate, but it will not like to accept any additional protons. So that one's out of the work. So it looks like we have 1, 4, and 5, which gives us C as the answer. So that, in fact, is the correct answer. So when we look at this, the one thing that could trip you up is maybe looking at this hydroxide ion, but note that because hydroxide ions are the strongest possible base, that they will not want to lose that extra hydrogen that's attached to it. Question number 40 says, the 2 species listed above that can be combined to prepare a buffer solution. Now remember, a buffer solution is a combination of an acid and its conjugate base. Now it has to be pardon me, it has to be a weak acid and a weak base combination, and those buffers are what can minimize a pH change. So, the 2 species listed above, well, we know that 1 and 2, those are conjugate acid-base pairs. However, this base is a strong base, so that won't work. So 1 and 2 won't work. 1 and 3 isn't even a conjugate acid-base pair, and it has to be a conjugate acid-base pair in order to work. Then it says 3 and 4. Well, 3 and 4 again are not conjugate acid-base pairs. Then we're going with 3 and 6, and 3 and 6 again are not conjugate acid-base pairs. So when we look, the best answer here is between 5 and 6, giving us a conjugate acid and its an acid and its conjugate base, and they're both weak acid, weak base. So our correct answer there is 40. For 40 is D. Okay. Let's take a look at a few more questions here. So this says we're looking for the value of Kb, and we're looking to see if this fluoroethanoic acid or acetate is a stronger base than one of these other entities listed. So it says Sodium fluoroethanate is a potent metabolic poison that is used to kill rodents. The conjugate acid of fluoroethanoate ion is fluoroethanoic acid. For this acid, the Ka is 2.6 times 10 to the negative 3. So, in order to calculate Kb, okay, we are going to use this formula again, where our Kb is equal to our Kw over our Ka. So it says the conjugate acid has a Ka of 2.6 times 10 to the negative 3. So when I plug this in, I have Kb equals my 1.0 times 10 to the negative 14 as for my Kw, and my Ka is 2.6 times 10 to the negative 3. Now when I plug that into a calculator, I get that my Kb is equal to 3.84, or 3.8 times 10 to the negative 12. Okay, so when I get that answer, I can automatically rule out questions C and D because they don't have my correct numerical value for my my acid and my Kb of those values. Okay, and then it says my fluoroethanoate ion is a stronger base than what? So when I look at my Ka values, I can compare my Ka values, and the lower the Ka value, the greater strength that base has. So when I compare my values for my Ka, okay, so my Ka of my fluoroethanoate ion is, let me just fix that here. Okay, so my initial Ka is this 2.6 times 10 to the negative 3. And when I look at my Ka for my H2PO4, the Ka is equal to 6.2 times 10 to the negative 8. Now I'm getting that off of my data booklet here, okay? So when I just take a look at my chemistry data booklet, I see that my Ka of my H2PO4 is, oh, sorry. I made a little mistake there. I need to find the Ka of my conjugate acid for H2PO4. So my conjugate acid would be H3PO4 with no charge, and my H3PO4 is, so for my H3PO4 is equal to 6.9 times 10 to the negative 3, and for my HPPO4 2 minus, okay, that's my 6.2 times 10 to the negative 8. Now, a reminder that the smaller our Ka values, the greater the Kb values, or the more basic the value. So the smaller the number, the more basic that value is. So when I look at the smaller values of my Ka, I see that my HPO4 2 minus has a smaller Ka value than the other two listed. Therefore, this has a greater base, or a greater base constant, or Kb. So therefore, the correct answer here is letter A. Alright, now if you were unsure about how to compare these values, you could in fact compare the Kb that you calculated up here and calculate the Kbs for both of these entities as well, and then compare them, and that's totally fine. However, you'll get the same answer regardless. Okay, let's take a look at 42. A brand of window cleaning fluid is composed of an ammonia solution, water, and a coloring agent, a very small quantity of soap. Okay, it has a 0.15 mole per liter concentration of NH3, and the pH of the fluid is blank. Okay, this is a situation where I may need to set up some sort of ice table. And I would just set up an ice table simply just as an organizational tool to make sure I'm on the right page here. So I set up my ice table like so, and I have a concentration of ammonia. So it says I have NH3, and I know I'm dealing with water, and I get my ammonium and my hydroxide. So we're looking for the pH, so we're looking probably to find something with our hydroxide ion concentration. Again, we don't include our water in our ice table, so I have my ammonia, I have my ammonium, and I have my hydroxide ions. Okay, and it tells me that my initial concentration of my ammonia is 0.15 moles per liter, and these are both going to be 0. Okay, and I have to figure out that this is probably going to be a plus x of some kind of value, and this is going to equal x. Okay, and I can figure out that my Kb for ammonia is equal to my Kw over my Ka. And when I look at my conjugate acid, okay, when I go into my chemistry data booklet and I look at my conjugate acid, okay, my conjugate acid here is ammonium, and the acid ionization constant for that is 5.6 times 10 to the negative 10. And my water ionization constant, so when I go to calculate that, I get that my Kb, I'm just going to write this down here, that my Kb is equal to 1.79 times 10 to the negative 5. So I can use some algebra, and again, that this value is just going to come down here. Okay, so I can calculate that if my Kb is equal to my products over my reactants, and my products are going to be x squared over my reactants, which is 0.15, equals my 1.79 times 10 to the negative 5. Okay, when I simplify that a little bit, okay, I get that, I'm just going to write it over here, x squared is equal to 2.68 times 10 to the negative 6. Okay, and when I square root that, I get that my x, where am I going to fit this in here? I'm just going to write this number on the other page here. So x squared, was equal to 2.68 times 10 to the negative 6. And when I square root that to solve for x is equal to 1.64 times 10 to the negative 3. Okay, so now that I know my value of x, when I go back to my practice diploma questions, or when I go back a few pages, I know that x is equal to my hydroxide ion concentration. Okay, if I'm looking to calculate my pH, okay, I can calculate that by calculating first my pOH, which is my negative log of my hydroxide ion concentration, which is equal to the negative log of 1.64 times 10 to the negative 3. Okay, so when I do that, I get that my pOH is equal to 2.79, and my pH is equal to 14 minus 2.79, giving me approximately 11.21. So when I look at the answer for question number 42, I see that D is in fact the correct answer. Okay, so when I go back and check my work here, again, when I look at my ICE table, okay, I did a little bit of a calculation to calculate for my KB. Once I got my KB, I could plug in my values into this algebraic expression. Once I found that, I could get the square root of this 2.68 times 10 to the negative 6. Once I did that, I got my value as x to be 1.64 times 10 to the negative 3. Now at this point, you could also say that if this was your OH value or your hydroxide ion value, you could also use your Kw to calculate your H3O ion concentration, which you could then plug into your pH formula. So either way, either method is again an acceptable way to find that answer. Okay, let's take a look at 43. The concentration of our hydronium ion concentration in a 0.040 mole per liter H2S solution is blank. Okay, again, I like to set up an ICE table just to ensure that I'm keeping track of what I'm doing here. And I may or may not use it, but it definitely helps me to get an idea of where I'm going here. So I'm just going to slide this over a little bit. Our formula is going to be H2S plus our water. And our H2S is definitely our stronger acid over water. So that is going to be our proton donor. So I should have hydrogen sulfide and H3O positive as my products. When I go to put this into my ICE table, I have my H2S, my hydrogen sulfide, and my H3O positive. Okay, my initial concentration is 0.040 and 0. And my change, or the concentration of our H3O, is going to be X of some kind. So we're going to be adding X, this is going to equal X. And again, in these acid equations, when we have to calculate for our hydronium ion concentration, we just carry that value down. We don't need to use our quadratic formula ever in a diploma setting. So when I do that and I check out my data booklet to see what my Ka is of H2S, let's see here. So I find H2S, which is right here, hydrosulfuric acid. I see that it is 8.9 times 10 to the negative 8. So my Ka is 8.9 times 10 to the negative 8. It's my Ka value. And again, I can have my x squared over my 0.04 equals my Ka value, equals my Ka. So when I simplify this, x squared is equal to 3.56 times 10 to the negative 9. And I'm going to then square root each of these numbers. And when I get my answer for X, which is our hydronium ion concentration, we get 5.97 times 10 to the negative 5. Okay, when I round that, I do in fact get answer B here. And when I check my answers, it looks like B is the correct answer. So I did end up using my ICE table as a thought process, and then I used that algebraic function again. Now remember, if you're ever solving for pH or your hydronium ion concentration, you always use this algebraic expression. Let's take a look at this last question here. Pardon me. It says, which of the following pH curves represents the titration of an acid with a strong base if one intermediate is produced? Okay, first thing we need to look at is we need to find the titration of an acid with a base. We should always start with a low pH if we're titrating an acid. So, if I ever see a high pH when I'm titrating an acid with a strong base, if I'm titrating an acid with a strong base, that means that my base is in my burette. So, with that said, I should have a low pH initially. So both C and D should be ruled out because I'm starting with a very high pH. So, when I look at the difference between A and B, it says one intermediate product or amphiprotic substance is produced. And when I look at B here, I just have my reactants and then my products with no intermediate. This change here is our pH change, but there's only our reactants and our products. Where with A, we see reactants and products, but this is an intermediate, which is then converted into our final product. A is the correct answer for 44. So, hopefully you can go back and rewind and pause at any time that you need to go over a question. Hopefully this was helpful for you to find some practice diploma questions. I do suggest going over some of these practice diploma questions prior to any exam and prior to the diploma for sure, because it will help you a great deal with understanding the formatting and the style of questioning that they will ask you, as well, pardon me, is you'll get an idea of the strategies to use when you're solving your diploma questions. So, good luck and